This is the second part of decoders. In the first part, we were covering this LCD display, and now we are going to continue applying this LCD display or connecting that one to a decoder, to the CD4543 decoder. As you can see here, there are 4 inputs where you can connect switch or jumpers from here to ground. And that's the first thing, to connect them to ground to Z number 0 here, to display number 0. In the practice, you can see here number 0, because the 4 inputs, which are here in blue wires or jumpers, they are grounded. So this is code 0, and that's in the code in 7 segments. So the decoder CD4543 is driving this LSD, or least significant digit. And the oscillator on your left side here, it's made of one NAND gate in feedback with a feedback loop made by this resistor of 300 kilo ohms and a 0.1 microfarad capacitor to ground. The oscillator is right here. You can see this is the gate H74HC132. This is the 0.1 capacitor to ground, the 200K resistor, a resistor between pins 2 and 3. And the other NAND gates are grounded. The second NAND gate, which is the inputs are here, is grounded. The output is left floating. This is ground for pin 7. This is pin 14, which goes to voltage. And the other 4 jumpers you see here are the rest of the NAND gates located on the right side of the chip. All unused pins, input pins, must be grounded to avoid oscillation. And in the decoder, the blanking input is grounded. We don't want to blank this digit. BSS goes to ground, BDD to voltage, and latch. The latch is transparent because we don't want to store any reading or any binary input at this moment. We just want the latch to be transparent. So it'll be decoding whatever we have here from 0 to 9. It'll be decoded into the 7 segments outputs, A through G, pins 9 through 14, 9 through 15. And notice that all the jumpers are located here. For example, pin 9 on the 43 goes to pin 14. So pin 9, which is this one, the yellow jumper, goes to pin 14. It is the yellow jumper. And the green jumper is pin 10. That one goes to 13. So the green goes to 13, and that's correct because this is 12, pin 12, and this is 13. Okay, so you can check all those colors and you will find that they are correct. So this is one of the practices or experiments you will be doing in the lab. Okay. Well, and there's another topic of encoders, but I don't want to cover that in this session. So I just want to cover that this is a very interesting experiment. Well, I forgot to say that the frequency generated by this oscillator is is within 100 and 200 hertz, and the display can work from 24, 25 hertz up to 500 hertz. So it is good to have these values, and this oscillator is driving the common and the phase. So the output of the oscillator, it is a red wire. It is pin 3, and it goes to the common on the display. And the common the orange wire goes to pin 6, which is the phase input. Okay, the decimal points here are not used, pins 5 and pins 9, but later we will see that in another video, in another application. And so when you are using liquid crystal display, the phase must be oscillating. Okay, and the signal must be a square signal, square wave signal. If it is not square, the display will be fading. Okay, and if it is too low the frequency, less than 20 hertz, you will see the display flickering. So this is why it has to be higher than 24 hertz and less than 500 hertz. Okay, this is the display from Lumex, and this is the practice that I'm expecting from everyone to do it. There are other capacitors you will see here, and these bypass capacitors, 104 or 0.1, and there is another one here. They are to bypass high frequencies and to reduce electrical noise in the bus, in the power bus. So every time you have a power bus, you need to put a bypass capacitor. But remember, this one is the capacitor for the oscillator. Okay. In another practices, we will drive the middle digit and we will drive the most significant digit using 2 more decoders. Okay. That's all for today. Thank you.